I started looking for what could drive the inflammation and injury to the kidney. And I realized there was a very big linkage with uric acid. And people with high uric acid were at really at increased risk for developing high blood pressure. And then we started doing experiments by raising uric acid in animals. And suddenly we found that those animals developed mild inflammation in their kidneys and high blood pressure just by raising uric acid. And then the question, of course, was, well, what drives up the uric acid?
Right.
And one of the things that can do it is sugar. And sugar intake had been increasing during the last century in parallel with an increase in uric acid and in parallel with a rise in blood pressure. And I thought, well, maybe that's it. And so we started giving sugar to animals, and they developed high blood pressure. And if we lowered uric acid, we could lower their blood pressure. But the incredible thing was, when we gave sugar to animals, they also became fat, and they became insulin resistant, and they became all these features that we call metabolic syndrome. And when we lowered the uric acid, we improved all of those. And they go, oh my gosh, could uric acid be important in the way sugar causes obesity? And sucrose is a disaccharide that consists of a glucose molecule and a fructose molecule bound together. And then when you ingest sugar or sucrose, the two get broken apart, and then you absorb them separately in the gut. So you get glucose and fructose together when you eat table sugar. And high fructose corn syrup is also consists of glucose and fructose that are mixed together in a combination that can vary in terms of concentration. Typically, it's like 55% fructose and 45% glucose. And these are the two major added sugars that are added to the diet, and they can make up 15% of the overall caloric intake in the average person's diet. So, sugar is a very big component. Of the two sugars, glucose and fructose look very similar in terms of structure and chemistry, but they are very different in the way they are metabolized. And so glucose is like the major fuel in our blood that we use to drive all the biologic processes we do in terms of, the major carbohydrate fuel. And fructose is not present very much in the body. There's only small concentrations in the body, maybe 1/100th or so of what glucose is. But the fructose, when you eat fructose, it's metabolized mainly in the liver and the intestine, but it can also be metabolized in other sites, like for example, in the fat, in the kidney, in the brain, and even in the islets and the pancreas, where insulin is made. So initially, when we were doing our research, we found that fructose was really the key sugar that was driving the obesity and metabolic syndrome. If we fed animals fructose, they got very, very fat, insulin resistance, fatty liver, high blood pressure. And the fructose was what was making the uric acid. So glucose doesn't make uric acid. But we also found, when we gave glucose to animals, they also became fat. But when we would lower uric acid in animals feeding sugar, we could have an effect. So it suggested to us that there was something going on with the glucose as well. So we realized that there is a pathway by which glucose can be converted to fructose in the body. And there's only one way in mammals, one way in humans that this occurs. There's only one way. And it's through a pathway called the polyol pathway. And basically, glucose gets converted to sorbitol, and then sorbitol gets converted to fructose. We realize that when you eat glucose, the glucose levels will be initially high in the blood and in the liver because it's like a high glycemic food. So when you eat the glucose, some of it spills over into the blood, and the glucose levels, which are normally like around 90, can get up to 120, 140, 150, even in a normal person if you're eating a lot of glucose. And that is known to be a stimulus for activating this polyol pathway. So what we did is we took these animals that were receiving high glucose diet, and we looked in their livers and found that they had turned on this enzyme to generate fructose. When you eat, the glucose gets absorbed through the intestine and into the portal vein. So the first organ it hits is the liver.
Mhm.
And the liver gets the brunt of what you absorb, goes to the liver first. And so the liver got this wave of glucose that activated this pathway. The liver started making fructose, and also some fructose even got into the circulation. But the glucose, the high glucose, when it would get to another organ, it also could stimulate fructose in other organs like the brain and the kidney. So the high glucose food was actually generating fructose. We did more studies, and we gave like a high fructose corn syrup to animals that could not metabolize fructose, and they were completely protected. So when you drink a soft drink, what's driving the obesity response, what's driving insulin resistance, seems to be the fructose that's in the drink and the fructose that you're going to make in your body. And recently there's a specialist in Switzerland who used radio labeled fructose and glucose to kind of figure out what was happening in people. And he's found that there is a lot when you give a soft drink to a person that you triple the amount of fructose you make. The uric acid is coming from purines, and purines are nitrogen containing substances that kind of are used as building blocks for DNA and RNA and energy. So the energy in our body comes from a substance called ATP, and it's really important. It's what drives us. We make energy, and then we use that energy to drive biological process, whether it's breathing, drinking, walking, talking, thinking. We're using ATP. And when ATP breaks down, it generates purines that get broken down further to uric acid. And likewise, when DNA, which is in the nucleus of our cells, and RNA, which drives protein production, these substances also contain purines. So purines, we think of protein, fat, carbohydrates, but there's also, what's in our nuclei, what's this DNA and RNA, and they're made up of purines and purine-like substances. And when they get broken down, you make uric acid. How do we make uric acid? Well, we can make uric acid from sugar. And it turns out that when fructose is metabolized, there is a breakdown of ATP. So the ATP starts to decrease and get broken down, and it generates uric acid. But other foods can also produce uric acid, alcohol, for example. And then you can make uric acid from foods that are purine rich. So that would be foods that have a lot of RNA and DNA. So things that have a lot of small nuclei in it, like sardines and caviar and things like that, they can have a lot of RNA and DNA. They have a lot of the cells are small. Yeast has a lot of cells and nuclei. And so like brewer's yeast can have huge amounts of RNA in it, DNA. And so when you make beer and it has brewer's yeast in it, the alcohol is making uric acid, but the brewer's yeast is too. Some meats also, have a lot of nuclei. And so some meats, not all meats, but some meats also can generate uric acid when they're metabolized. Some plants have a lot of cells, cellular RNA and so forth, and they can also make uric acid. Okay, so you can make uric acid from food. You can produce uric acid like from overexertion and so forth, where your muscle breaks down a little bit, and so you release DNA and so forth. So you can make uric acid, with severe exercise, for example, and modest exercise actually lowers uric acid. Most people think of uric acid as the cause of gout. So gout is this disease where with the uric acid levels get up high in the blood, the uric acid can crystallize because it's poorly soluble. And when it crystallizes, it typically crystallizes in joints. It loves the big toe because we're walking on it, and there's oftentimes the toe has a little bit of damage from years of walking on it, so that the crystals can deposit there a little bit easier than other sites. Gout becomes the classic disease that people think of when they're getting their uric acid checked. I've had patients contact me who were having trouble losing weight, and they were eating natural fruits, but eating huge amounts. And they were very sweet fruits. And mango is one of the sweetest ones. Pears, apples, these tend to be grapes. They tend to be high in sugar. A bowl of grapes, you can eat a lot of sugar in just a few minutes and overdo it. And I would probably eat like one fruit at a meal and separate it out so that you're not eating a huge amount of fructose all at one time. And the other problem is like fruit juice. When you take the fruit and you put it in a juicer and you remove a lot of the fiber and a lot of that, and in the process, you make this drink that has multiple fruit in it. And now you can get 20 grams of fructose and you drink it fast. And boy, that combination can really activate this process that causes the fat gain.
And I also think it's because we eat fruits that are bred to be sweeter and bigger. So we are not eating the fruits that our ancestors ate long ago. And fruit is available 24/7 in every single variety you want now. And so long ago, that would have been great for us, but not as much now.
A lot of people who are super athletic, these super athletes, a lot of them, they say they can eat anything they want and get away with it. Some of the people that are really champion athletes, they can eat sugar and they can eat anything they want, and it doesn't seem to affect them. What's happened is the way that sugar works is it damages the mitochondria, which is what makes the energy. And so the mitochondria are your main things in your body that are making the ATP. And when they're making this ATP, they produce it. You can turn it down if you want by creating oxidative stress. If you create oxidative stress in the mitochondria, and that's what uric acid does, it kind of dampens the amount of energy that's made. And in turn, the calories that are coming in, instead of going to make ATP, which is the immediate energy you need, it gets shunted to make stored energy, which is fat. So, when you eat calories, it's really like eating energy. And it can either be used to make immediate energy like ATP, or it can be stored as energy where it's being stored as fat. The way that fructose works is that it generates this uric acid, and the uric acid kind of stuns the mitochondria with a little bit of oxidative stress, and that shifts the energy from being made from ATP to being stored ATP or fat. So these super athletes, they have fantastic mitochondria. Their system's so strong that it's very hard to knock it down. If you eat a soft drink, you can have this oxidative stress, but the mitochondria are so strong that you can't notice it. But the worry is that if you do this again and again and again, that it's going to, over time, cause damage. And the way the systems are worked, there's a lot of defense systems in place so that when you're eating things like glucose, when the glucose is being metabolized, there is some energy being spent, but the body tends to be able to maintain the energy levels always in a normal range. But like if you eat glucose or if you eat protein or fat, it tends not to drop the energy in the cell. But when you eat fructose, it's very different. And what fructose does is it gets metabolized so fast that there's an acute rapid consumption of ATP. It's not regulated. So if you get a big dose of fructose, you get a big drop in ATP. If you get a small dose of fructose, you get a smaller drop in ATP. So it's sort of related to the amount and the concentration of fructose that gets to the liver. So if you drink a soft drink that has a lot of fructose and you drink it fast and you drink it on an empty stomach, it's like a wave of fructose that gets to the liver, and that triggers a big fall in ATP. Now, when the ATP falls, there's also a fall in intracellular phosphate that accompanies it. Use the ATP, the phosphate comes off, and you make ADP, and then another phosphate comes off, and you make AMP. And the ADP and AMP get reconstituted to ATP. But when the intracellular phosphate falls, the sweeper system comes in that removes the AMP. And so you can't reconstitute the ATP very well. That sweeper system is this purine degradation system. So it breaks down the AMP to IMP and all these things and eventually generates the uric acid. And then the uric acid comes back and goes into the mitochondria and causes oxidative stress that keeps the ATP production down. The effects of that is to shift ATP production to another system that doesn't require oxygen, that's called glycolysis. And it also stimulates fat production, insulin resistance, and a whole series of events that are associated with that animals would like to have to help them survive. And to survive, you need to have enough energy. If food is providing you energy, but if there's no food, then you have to live off your stored energy. Right. And the stored energy is the fat. So all the animals want to have some fat, which is the reserve for when things are bad. So animals all carry a little bit of fat, but you want to be fat enough that if there's no food or a big storm comes and you can't eat for 2 weeks, that you can survive. Now, some animals know that there's going to be a long period of time without food, like a winter or like a bird that wants to migrate 5,000 kilometers or something without stop. They have to have enough food. So they have to store extra fat. The way they do this is they eat things that can either make or that contain fructose. What that does is then the fructose drops the energy in the cell and it keeps the energy at a lower level. And that's like an alarm signal. The animal says, oh my God, I don't have enough energy, even though it does. It has stored fat, but it's tricking the system into thinking there's not enough energy. And that activates all kinds of processes. It's foraging, hunger, foraging for food. You become insulin resistant as a protective mechanism. Insulin resistance, these animals that like hibernate become insulin resistant because what happens is they reduce the glucose uptake in their muscle so that it's preferentially available for the brain because the muscle uses insulin to take it up. And so when it becomes insulin resistant, it can't take up the glucose into the muscle as well. So the glucose goes up in the blood. But the brain, much of the brain doesn't require insulin. So as the glucose goes up in the blood, it becomes a fuel for the brain. What's interesting is the fructose drives this signal. So it activates this process, but it doesn't actually necessarily make you fat. It just makes you hungry and insulin resistant. To really gain fat, you have to create this insulin resistance and leptin resistance, and so that you're hungry. And then you have to provide the food, particularly like high-fat foods have a lot of calories, 9 calories per gram. They're energy dense, so you can get a lot of calories very quickly. So if you eat fat with fructose, if you eat sugar to make you act as an alarm signal, and then eat a lot of fat, you can really gain weight. So if you give animals fructose, they become fat. If you give them a high-fat diet with the fructose, they become real fat. If you give them high-fat diets without fructose, they don't really get fat. But in general, the meat diet would be very good because so you're not eating a lot of carbs, and so you're not activating the switch. And the endogenous pathway where you make fructose in your body, you make it from glucose. So a low-carb diet also kind of protects you. A meat diet that has very minimal carbs, that would be a good way of blocking making fructose as well. So it would work fairly well, I think. So, but you're right. If you ate a pure meat diet, but you allowed yourself to eat a lot of fruit, you'd have to be careful that you don't eat so much fruit that you're activating the switch. So uric acid is particularly generated from organ meats like liver and so forth. So, I know that currently you're not a big fan of eating a lot of liver. And I agree with you because not only does it contain vitamin A and copper, but it can generate a lot of uric acid. And it also it's one of the main organs that concentrates toxins. So any toxin that the animal might have eaten.
I've just seen too many clients where they eat liver because it's a superfood and they're eating multiple ounces in a day. Sometimes it's even 1 ounce in a day. And depending on your liver health And then depending on your uric acid and your insulin resistance and metabolic syndrome, it becomes an adverse food for many people. And I really, really appreciate you talking about how purines in meats and then the addition of fructose is just not ideal.
When we were doing our studies, we had this discovery that the way fructose was activating this pathway wasn't from the calories of the fructose. It was from the energy, the fall in energy that occurs. So when the energy falls, if it falls a lot, then you trigger a big switch. You trigger a lot of insulin resistance and the process that leads to obesity and so forth. What drives the energy down is the concentration of fructose that gets there. So if a lot of fructose gets there quickly, it's going to cause a greater drop in energy than if it trickles in. So like, for example, so we started doing studies like if you take a soft drink and you drink it in 5 minutes, or if you drink it in an hour, is there a difference? And so it turns out like if you drink it all at once, you get this big drop in energy and you activate this biologic switch big time. If you could drink it very, very slowly over an hour, the activation of the switch is much less. I do want to bring up another point, which is that a very simple thing that you might consider doing to try to bring your uric acid down or to block any negative effects of the uric acid is to drink water, a lot of water. So we found that fructose drops the energy in the cell, and that seems to be the special mechanism by which it drives obesity. And the way it works is that when the energy falls, that there's the breakdown of ATP is broken down to uric acid, and uric acid is doing all these biologic effects. And so for the longest time, we thought it was just that pathway that was driving the obesity. But then we had the discovery that there's another mechanism that's linked with the uric acid driving the obesity. And that pathway seems to be due to the fact that fat is more than just an energy source. So we think of fat as a source of calories that animals use when there's not enough food around. But animals also use fat to produce water. And the way that works is when fat is burned, it generates water. So there's no water in fat, but when you burn it, you produce water. And a lot of animals turn out to make fat to not just store it as energy, but to store it as water. So when there's not enough water around, they can have it available. When we realized that fat was also a means for storing water, we became interested in if you're dehydrated, would that be a mechanism for stimulating fat? Because if you were afraid you're going to become dehydrated or you were dehydrated, wouldn't it make sense to try to store fat as a source of water? Whales will have a lot of fat. They don't get their fresh water from the seawater. They have to get their fresh water from the crustaceans and things they eat. In order to get enough water, they actually get fat. And then what they do is they break down the fat to release water. And so it turns out that dehydration is another mechanism for generating fructose in the body. So if you eat like salty foods, a lot of salty foods, that will activate this enzyme to convert glucose to fructose. And when you eat salt, you basically are becoming dehydrated. That's why you get thirsty. So you eat salt, get dehydrated, you start making fructose. The fructose drives fat production, and then the fat production becomes a source of water. So if you have a lot of fat, you can live without a lot of water because you can use the fat to make water.
If I understood you correctly, dehydration can actually endogenously within the body produce fructose.
Absolutely.
I think that's fascinating because a lot of carnivores, since we don't eat a lot of carbs with fat, with salt and sugar, we don't feel a lot of thirst. So they're maybe getting dehydrated and then they're producing some of the fructose, which is making some people stall in their weight, even though they're eating very low carb.
And so what we found is that dehydration actually is another mechanism that turns on this polyol enzyme to convert glucose to fructose. And when you become dehydrated, mild dehydration triggers this effect to try to make fat. Salt then becomes another mechanism to drive obesity, and it works though through carbs. If you have glucose and you activate this enzyme, the glucose gets converted to fructose. So like if you're on a pure protein diet, a meat diet, you're not eating a lot of carbs, you're not going to have a lot of glucose around, and the salt won't be as powerful as a mechanism to generate fructose because you don't have the huge amounts of glucose in your system. Most people who are obese show signs of mild dehydration. And most people who are obese have an elevation of a hormone in their blood called vasopressin. And you can measure it. It's called copeptin. And Judy, you may want to measure your copeptin level, to honestly, because the copeptin level, when it's high, it is absolutely a risk factor for obesity. And it reflects this hormone vasopressin. And so we were interested because vasopressin holds on to water, and it does so by concentrating the urine. So we thought to ourselves, well, maybe vasopressin might actually increase fat production as a mechanism, as another mechanism to hold on to water. And so we did a whole series of experiments, and we had a very big discovery, which was that the vasopressin actually drives fat production and drives the metabolic syndrome. So fructose is driving uric acid and vasopressin together, and those is driving the obesity and metabolic syndrome. Sugar, fructose, is driving this very grand pathway that involves uric acid and vasopressin. So when you measure your uric acid and it's high, a question that I would want to know is, is your vasopressin high as well? And if so, maybe this is, trying to keep you normal by trying to keep your glucose levels up, and maybe it's trying to keep you normal that way. But it is a little worrisome if they're really both high. And the interesting thing is you can suppress both by drinking water. So if you drink water, that can turn off the vasopressin. And so people who are overweight don't realize that they're not drinking, many of them are not drinking enough water. I recommend at least 6 to 8 glasses of water a day for pretty much everybody. But you don't want to just increase water because it is possible to intoxicate on water. You can drink so much water that you can get into trouble. Everybody probably needs to discuss with their doctor how much is safe for them. Relates to how much work you're doing outside and all these kinds of things. But I would say that 8 glasses of water is very healthy for the average person. And if you're going to drink a lot more than that, you probably should talk to your doc. When you're on a meat diet, the BUN will be slightly high just from that. And we're not really worried about the BUN at all.
Okay.
And if you're muscular, your creatinine may go up just because creatinine not only reflects kidney function, but also reflects muscle mass. So if you're very muscular, you may have a slightly elevated creatinine. Meat and protein can make the kidneys have to work harder. Sure. And so over time, it can, particularly if you already have kidney disease, you have to be a little bit careful about a high meat diet. Gout correlates, the higher the uric acid is, the higher the risk for developing gout. But there are people who had gout with normal uric acids, uric acids of 6. And there are a lot of people who have uric acids of 9 who've never had a gout attack. But typically, when the uric acid gets around 7, there's an increased risk for gout. And so a lot of people will go by the fasting uric acid levels. But uric acid levels do go up and down during the day. And like if you eat a purine-rich or a sugar-rich meal, your uric acid can go up. And with sugar, the uric acid tends to go up like 15 minutes to 60 minutes after you eat it. But a purine meal, the uric acid kind of peaks more like 2 to 4 hours after you eat it. And so there is some variation. And so the classic people who get uric acid attacks, they'll tell you that, they ate a particularly bad meal, then they went to bed, and at 3 a.m, they wake up with a gout attack. And also there's this thought that when you start a medication to lower uric acid, that the shift in uric acid, that the shift may be enough to trigger attacks. So it's thought that the main risk for gout is the level of uric acid, but it's also known that the shifting is important and can play a role in triggering attacks. Main worry with high protein diets and kidney function are really in people who have established kidney disease. It's really been the problem in people who have really significant kidney disease, what we call like stage 3 or stage 4 kidney disease. That's where you really do need to be careful with how much proteins you're eating, because proteins can cause an increase in pressure in the filtering units of the kidney. So the kidneys have like 1 million little filters per kidney. And when you eat high protein diet, it tends to increase the pressure transiently in those filters. And it turns out that uric acid does some of the same things. So when you raise uric acid, it increases the pressure in those filters. And normally the kidney can handle that pretty well. But if it's damaged, it's already got, when the kidney's damaged, the filters that are left usually filter under higher pressure to try to maintain filtration.